So sometimes the most difficult part of solving a differential equation is remembering the algebra and or the calculus that you need in order to actually execute the solution process. So this is an example of a separable differential equation, but it's going to need partial fractions in order to solve it. So we'll work through the example, and hopefully this will refresh your memory about how partial fractions works in this context. So here's our equation, and so in order to separate the variables, we're going to divide this equation by 1 over x, or multiply by 1 over x, and we're also going to multiply by dx to get the x's all on the other side of the equation, and then we're going to divide by all the y's on this side of the equation so that they show up on the other side. Now, it might be tempting to want to simplify the algebra here and just divide by dy and put it on the other side of the equation. But we can't integrate with dx and dy in the denominator. They have to be on the top, in the numerator. So even though it's a little bit more steps, this is what we have to do. So I'm just going to copy my equation, and we're going to multiply both sides of the equation by 1 over x, and we're going to multiply by dx. And we're going to do that on both sides. And then we're also going to divide by y and y plus 2 on both sides. And so we're also going to multiply these over here. Okay, and so now we can cancel. So the x cancels with the x, and over here we're just left with 1 over x and dx. The dx cancels with the dx, and then over here the y and the y plus 2 cancel, and we're left with 1 over y plus 2 dy. And on this side, 1 over x dx, after simplifying. Let's just break a space. Okay, so once we have it in this form, the right side of the equation is easy to integrate, but this side of the equation we have to break up in order to do the integration. And so what we want to be able to do is we want to turn this 1 over y plus 2 into some number over y plus some other number over y plus 2. So this is our partial fraction step. So recall what we have to do is we have to write this side of the equation as a common denominator. So a times y plus 2 plus by, and then our common denominator is y and y plus 2. So this is our cross multiplying step. And as a consequence of that, we set, since the two denominators are equal now, we set the two numerators equal to each other. So 1 is equal to ay plus 2a plus by. So I've just distributed through my denominator. Now remember that in order to solve for this, we're going to let the y constants on y coefficients on one side of the equation equal to the y coefficients on the other side. So in this case, we have a and b multiplied by y on this side, but 0y on the other side. So this is equal to 0. And then the constants are equal to each other. So 2a is equal to 1. And so we have a fairly simple to solve equation. If 2a is equal to 1, then a is equal to 1/2. Oops. And then as a consequence, if a is 1/2, then if a plus b is equal to 0, we know b has to then equal -1/2. So now we go back up to this equation right here, and what we're going to do is we're going to rewrite this side of the equation as 1/2 divided by y, and 1/2 divided by y plus 2. And this is, sorry, a minus sign in between them, because this is minus 1/2. Okay, so now we're going to integrate both sides. So again, copy. We're going to integrate this side of the equation. And we're going to integrate this side of the equation. Now the left side of the equation, we can pull the 1/2 out. There we go. We can pull the 1/2 out. And so we have 1 over y minus 1 over y plus 2 dy. And then on the other side, we just have our integral of 1 over x. Now obviously all of these are natural log terms. So we're going to have 1/2 and then log y minus log y plus 2 is equal to, bracket, equal to log x plus c. So we only have to put the constant of integration on one side of the equation, but then we need to start simplifying. So this side of the equation, we can combine these two log equations, 1/2 ln into y over y plus 2 equals ln x plus c. Now I've dropped the absolute values here, but kind of keep in mind that they're still there if y is negative or if x is negative. But for right now I'm going to assume they're positive. And then the 1/2 power in front of the log on the other side then becomes a 1/2 power inside the log. And so this whole expression there gets put under a square root. And the c constant over here, what I can do is I can rewrite it as ln e to the c. There we go. And then I can combine these two log expressions together. E to the c is just some other constant, so I'll call it, let's say, d. And so when I combine these two log expressions, I will multiply by d. And I'll just kind of put a note over here. E to the c is equal to d. Now that my two sides of the equation have log and log on the outside in both cases, and they're not multiple terms, now I can cancel the log and just take my square root. 1 Not the log part, just the square root part. Well, we can start over. Y over y plus 2 is equal to dx. And so now the logs are canceled. Now, this is an implicit expression. We could solve for y exactly if we wanted. We would square both sides, and so we would get something like y over y plus 2 is equal to, if d squared is equal to e, then x squared, and then you would multiply by y plus 2 on both sides, get y equals y plus 2 times e to the x squared, which is equal to y e x squared plus 2e x squared. That's a big E. And then you would put the y's all on the same side of the equation. Y minus y e x squared equals 2e x squared. And then you would factor out the y. 1 minus e x squared. And then you would solve for y by dividing. Y equals 2e x squared all over 1 minus e x squared. Now, normally I don't expect my students to do this, but I wanted to do it in this particular instance because this equation can also be solved with the Bernoulli approach, and so just to verify that we get the same answer, I did it in this form.